Hello guys, in this tutorial let's talk about chemical kinetics. So I'm going to make it as simple as possible for everyone to understand, and I'm trying to attempt to exhaust most of the concepts under chemical kinetics in just 30 minutes. Okay, so basically what is chemical kinetics? So chemical kinetics is actually involves studying how fast a chemical reaction progresses. Okay, how fast a chemical reaction is what? Progressing. So that's what chemical kinetics deals with. Okay. So apart from how fast a chemical reaction progresses, chemical kinetics also deals with reaction mechanisms. Okay. And reaction mechanisms. So reaction mechanisms actually explains how exactly a chemical reaction happens, a series of steps that are involved for a chemical reaction to take place. Okay. So what are some of the things that we need to understand under chemical kinetics? So we need to understand that we are going to be working with reaction rates. Okay. So how fast a chemical reaction is going to progress. Also, how fast a reaction happens is what we call the reaction rate. So reaction rate, which we are going to denote by rata R, is going to be given as a product of K and what? The concentration of a certain reactant. Okay, so this is an equation that is helping us understand what really is going to be happening. So it means that the greater the constant K, the greater the rate of the reaction. Okay, the lower the constant K, the lower the rate constant, or the lower the rate of the reaction. Okay, so we need to understand that this K, which is affecting how fast a reaction is going to progress, is dependent on some of the factors that we are going to talk about. So what are the factors that the rate constant depends on? So the same factors that the constant depends on are the factors that the reaction rate depends on as well. So what are these factors? So I believe from high school we've talked about the factors that affect how fast the reaction progresses. So these include temperature. Okay. So what are we saying? So generally speaking, at higher temperatures we expect that the reaction is going to act faster. Okay. So at higher temperatures the reaction rate is going to be faster. So the K constant is greater at higher temperatures. Okay, so why is it so? So there is what we call corrosion theory, which explains why it is important for the temperature to be greater. So the corrosion theory tells us to say that when two reactants react in a chemical reaction, so when you have two reactants in a chemical reaction, so when two chemicals react, their molecules have to collide for a chemical reaction to occur, and these must collide with sufficient energy. So that's what the collision theory tells us. Okay, so there must be collision. So particles must collide for a chemical reaction to occur, and they must collide with sufficient what? Energy. So this energy is what we call activation energy, which we are going to talk about as we talk about the Arrhenius equation. Okay, so we know that the temperature, we define temperature to be the average internal kinetic energy of what? The particles. So we define temperature to be the average kinetic energy of the particles. So meaning as you increase the temperature, you are increasing the kinetic energy of the particles. And we say that kinetic energy is actually the energy that defines something that is in motion. So the greater the kinetic energy, the greater the movement of the particles. So that means that as we are increasing the temperature, kinetic energy is going to increase. And as we increase kinetic energy, more successive collisions will occur. and therefore the reaction is going to be faster. That's why the temperature is important. So at that temperature, the rate of the reaction generally increases. Okay, so the issue of increasing temperature, increasing the kinetic energy is what we call the kinetic theory. Okay, what else affects the rate of a chemical reaction or the rate constant? So the concentration. So the concentration is also one of the important factors that affect the rate of a chemical reaction. So what is the concentration? So concentration, usually we talk about it in terms of molarity, where we are saying it's the number of moles that are dissolved per liter of a solution. Okay, so the greater the concentration of the reactants, the greater the concentration of the reactants, the greater the number of collisions that are going to occur. Okay, so whenever the concentration is greater for the reactants, we expect that the reaction is going to be faster. The likelihood or the probability of the particles colliding is increased when the concentration is higher or greater. Okay, so in summary, the greater the concentration, the greater the what? The greater the rate constant. Okay. Now, the third point. Catalysts are one of the factors that affect the rate of a chemical reaction. Okay. So what is a catalyst? So a catalyst is actually, it's a substance that speeds up. It will speed up the rate of a reaction. So how does it speed up? It speeds up by lowering the sufficient energy required, which is the activation energy. Okay. So the catalysts themselves are not used up. Okay, they just lower the activation energy, so the reaction will be faster in such a case. So they lower the activation energy, thus increasing the rate of a chemical reaction, because only a little energy is going to be required. Number 4, the surface area of solid reactants. So the solid reactants with a greater surface area are expected to react more. So when you have something small, and when you have something bigger, so which one is easier to dissolve? Okay, let's say you have bigger solid particles and the ones that are smaller. So which one is easier to dissolve? So it's easier to dissolve something that is crushed or small crystals than things like that. So why? It's because a particle that is small is going to react, or is going to be colliding with the other substance from different parts. But in a case of something bigger, there are a lot of particles inside there that are not going to be colliding with the other reactant. So the greater the surface area, the greater the rate of a chemical reaction, because more collisions are expected to occur. The reactants will be more in contact. Unlike when something is big, the particles inside will not be able to be in contact with the other reactants. Number 5, the pressure of the gaseous reactants. So in terms of the gaseous reactants, pressure affects. So we expect that when something is there's more pressure there will be more collisions. Okay, so thus it is also going to increase the rate of what? The chemical reaction. Okay, so I hope you are following, even as we get to move and talk about the reaction rates more in detail. Okay, so we've talked about the factors that affect the rate constant. So now let's try to talk about the reaction rate more in detail. So reaction rate. So we are saying the reaction rate it can be determined by monitoring the change in concentration of either the reactants or the products. So if you have reactants A and B giving us products C and D, okay, so their reaction rate or the reaction rate of this reaction can be determined by either monitoring how fast the reactants A and B are changing, or how fast they are reducing, excuse me, or by looking at how fast the products C and D are forming. So by just looking at that, you're able to predict or determine the reaction rate. Okay, so there are two ways, in short, two ways of predicting the reaction rate. One way, which I've said, is how fast the reactants disappear. Then also the second one, where we're saying how fast the products form. So from that, you're able to predict, of course, in respect to time. You monitor the change. For example, you say you are the concentration of 2 molar concentration of A. After maybe 10 seconds of a reaction, you find that it has reduced to maybe 0.5 molar concentration. So you're able to determine the rate of reaction by looking at the change divided by the time. Okay. So now we need to know how to express this in terms of an equation. Okay. So let's say you have the same reaction that I wrote. Reactant A reacting with B to give us C and D. And let's say the stoichiometric coefficient in this case are A, B, C, and D. Okay, so let's say those are the stoichiometric coefficients. So how do you express the reaction rate? How are you going to write it? Okay, so the rate of the reaction in terms of the reactants, we are supposed to put a negative. So it's going to be negative of the change in concentration over A over the time that it takes. Okay, multiplied by A, which is a stoichiometric coefficient there. Okay, so we can also say this is also equivalent to, somebody else may say, okay, you are looking at the issue of reactant A, me I'm going to look at B. So I can say it's also -1 over the stoichiometric coefficient B multiplied by, let's say, change in B, the change in concentration of B divided by the time that is going to take. Well, somebody else can also say, okay, me I'm going to look at how fast the products are forming. So it can be equivalent to, so for the products we don't show a negative, so it's 1 over C multiplied by the change in C over the time. Then somebody else may say, okay, me I'll look at D, so it still be 1 over D multiplied by the change in concentration of D over what? Over the time. Okay, so why are we putting a negative? So let me try to explain why we're putting a negative by showing it in terms of calculations. So our goal is to make sure that the rate of these reactions are always going to be what? Are always going to be the same and equivalent. Okay, so let's say at the start of a reaction, you add the 2 molar concentration of A. Okay, then after some time we expect, of course, that the concentration is going to do what? It's going to reduce. Maybe it reduces to 0.5 molar concentration. Let's say in a time of maybe 2 seconds. Okay, let me make it maybe 10 seconds. Okay, so in such a case, assuming our stoichiometric coefficient there is maybe 2, the rate in such a case can be given by -1 over the A, which is 2 in this case, then the change in A over change in what? over change in time. So this is going to be negative 1 over 2. Our A initially was what? 2. So it's actually the final one, which is 0.5 minus the initial, which was 2, divided by the time, which was 10. Okay. So the idea is to make sure that the rate is always going to be positive. So if you say 0.5 in brackets minus 2, it's going to give us a negative 1.5. So that negative multiplied by the negative outside, it will give us a positive 1.5 divided by 20, which is a product of 2 and 10 there. So 1.5 divided by 20. So what I'm getting is 0.075. So remember, we had the concentration of M, so it's going to be molarity per second. So this is actually the common way of expressing the rate of a reaction. Okay. So now let's say you have this reaction. Okay. Giving us 4 nitrogen dioxide plus oxygen there. How do you express the reaction rate? So our reaction rate in this case can be determined by either looking at the reactant or the product. So in terms of the reactant changes, so we'll put a negative 1 over the stoichiometric coefficient 2, then its change in concentration. So I'll say change in concentration of that reactant over the change in time. You can also write it in terms of the product, which is going to be 1 over its stoichiometric coefficient, therefore, multiplied by its change in concentration, divided by the change in time. Or, for oxygen, the stoichiometric coefficient there is 1, so it's going to be just change in oxygen over what? Over change in time. So that is the way. So these are the 3 major ways in which you can deal with predicting the rate of a reaction in such an equation. Okay. So now let's try to look at what we call rate laws. We know we've already talked about the issue of the reaction rate. So how about rate laws? What is a rate law? Okay. So each reaction has its own equation that will express the rate as a function of the concentration. Okay, so you might have come across something like this. Let's say the rate of a reaction for this equation, maybe for this reaction, maybe you are told maybe the reactant in such a case, let's say A and B are reacting to give us C and D. So they may give you an equation to say, okay, the reaction rate of this reaction is dependent on this equation. They put A and maybe B. So that is an example of a rate law. Somebody else, you may also might have seen something coming out like this. Okay, it can come out, it can just be dependent on one reactant as well. So it can be A, maybe raised to the power of 2. So that is also an example of a reaction rate law. So it's just a function of, it expresses the rate of a chemical reaction as a function of its concentrations. It can be the concentration of the reactant or the products. Okay, but usually we tend to work with the reactants. Okay. So rate laws are usually determined experimentally. Okay, so we usually tend to determine the rate laws used in an experiment from the experiment data. We don't look at the stoichiometric coefficient. Of course, there may be coincidences where you have A and maybe reacting with let's say 2B, okay, giving you maybe C plus D. So the rate law, it may be coincidental, by coincidence, that the rate law is maybe, let's say, constant K multiplied by A, then B squared. So it's not it doesn't necessarily mean that it is coming from the stoichiometric coefficient there, the 2, because there are cases, for example, where you have this reaction. Okay, so it has been proven experimentally that the rate of this reaction is actually given by K. Then we have fluorine 2 multiplied by, so here the power is just 1. Okay, despite it having a 2 there. So the ratio doesn't depend on the stoichiometric coefficients. Okay, it's independent of that. Okay, so I want you to know that we have got what we call orders of reactions. Okay, so where you have got the ratio coming out like this, okay, so you add the powers of the reactant. So in this case, I can say this is first order, because we just have what? I just have 1 there. It's a first order reaction. In a case where we say, okay, in this case the rate is maybe A squared, the concentration of A to the power 2. So that is second order. Second order can also be you have 2 different reactants. So you add 1 plus 1. It tells you that is what? Still second order. So if you have a different power, maybe 2 there, 2 plus 1, it gives you a third order reaction. But in this study, we are going to focus more on the first order and the second order of the reaction. Okay. So the equations that are going to be very helpful when it comes to dealing with the rates of reactions are these. So we're going to start with 0 order. So for a 0 order reaction, what is it going to be dependent on? So the equation that we're going to be working with is, when you look at the concentration of you've been given the concentration of a reactant in a 0 order reaction, you find that the equation that you're going to be working with to determine, to predict maybe the final concentration is going to be this equation. So the final concentration in a 0 order reaction is going to be given as negative. Let me use something different. Let me do this. Okay. So let's say F final is equal to A initial, then minus. Okay. So we use the square brackets to show concentration. Okay. So this equation is going to be working for the 0 order reaction. So where Fi, this is your final concentration of the reactant. Then you have got the initial one there, subtract the constant K multiplied by the time T. Okay. How about first order reaction? So for a first order reaction, the equation that we're going to be working with is going to be this. Okay. So a first order is going to be dependent on the natural log of the final concentration. Then the natural log of the initial concentration, again minus K multiplied by the time. So what is the concentration there? So that is for the first order reaction. Then for the third order reaction, what you need to know is, for the second order, here the gradient is different. Okay? Here the gradient is different, and it's going to be in terms of refraction. So it's 1 over the final concentration, 1 over the initial concentration, plus, here the gradient is positive. So these are the three major equations that you should understand. From these equations, we are going to understand how you predict the half-life of different reaction rates. Okay. So now, how do you predict the order of reactions? How do you get to determine the order of reactions? So the order of reactions are going to be predicted from the experiment data. When given experiment data, you can also predict it by looking at the units for the constant K. Okay. So let's say we have experiment data here. Okay, let's say we have our time there. Let me come up with a table. Then we also have the concentration of sodium. It's a nitric dioxide in molar concentration. Then our time is in seconds there. Okay. So initially you've been told the time is 0.0. Then it's 0.01. That's the concentration at that time. So after some time, when it was 50 seconds, the concentration went to 0.0787. Then after some time, it reduced to 0.0649. Then after some time, it reduced to 0.0481. After 100 more seconds, it became 0.00. Okay. So here's supposed to be 0.00. There's some zeros there. Let me write it better off. I'll copy that again. Okay, so for 50 seconds, it's supposed to be 0.0787. For 100 seconds, it's supposed to be 0.0649. For 200 seconds, it's supposed to be 0.00481. Then for 300, it's supposed to be 0.038. So these are the concentrations after a certain period of what? A certain period of time. So how do you get to predict now the reaction order there? So the first method that we are going to work with is by looking at the graphing. Okay, we need to sketch the information that we've been given. We see what we are going to have. Okay, so remember from the equations that we had, we are saying our zero order reaction is supposed to be something that is supposed to come out like this. We said the equation is the final concentration is equal to the initial concentration minus Kt. Okay, so consider that part to be the gradient. Consider that part to be the gradient. So this one is supposed to come out like this when you have a graph like that. Okay, the same applies to, excuse me, the same applies to the second order reaction. That's the way it's supposed to come out. It's also a negative. The only one that goes up is the final one, which is the second order reaction. So now let's try to predict now. Let's try to predict. What piece of information do we have here? Okay, so generally what we have is, let's say this is our graph. Let me put it so. Okay, so this is our y-axis. This is our x-axis. Okay, so our time, what do we have? We have from 100 up to 300. So say 100, 200, and what? 300. Okay, so basically if you begin plotting this information, how is it going to come out? So compare the values that you have. 0.01 is bigger than all these numbers that are down here. Okay, it's bigger. So meaning that initially at 0.0 there, you are starting from somewhere there. Okay, after some time, so what was at 0 somewhere there? Let's say that's 0.01. After some time, where is it going to be? So it's going to reduce a bit. It's going to 0.078. Okay, let's say somewhere there. Okay, then after some time it reduced to 0.06. That is after 50 seconds. 200, 300, okay, 300 is 0.038, somewhere there. So this is the way it is coming out. Okay, but our goal is to make sure that it comes out to be a straight line. That is what we want. We want it to be a straight line. Okay, so I'm just trying to give you ideas on how you should sketch it, but on a graph is supposed to be actually something that is supposed to be exactly what you want. Okay, so whenever it doesn't give you a straight line, so this is plotting for testing whether it is if it gives you a straight line in this case, then you can make a conclusion to say what you have is what is going to be a zero order reaction, because this is the one that we are looking at in terms of just the concentration itself without anything else. Okay, so that is the way you are supposed to work out with. So in a case of second order reaction, you are supposed to plot a graph of since the equation is natural log of A final being equal to the natural log of A initial minus KT. In this case, you're supposed to plot the natural log of the values you're trying to test. It's a test and error thing of a piece of information that you have. Okay, and time. So you come up with the natural log of the concentrations, then you come and plot. So if it gives you a straight line going down, then it proves that it's first order. If it doesn't come out as a straight line, then it's not first order. For second order, the equation itself is telling us that it's 1 over the final concentration being equal to 1 over the initial concentration minus what? So here it's actually under summation plus KT. So in this case, from the gradient there, this one is supposed to be going upwards, and only if it comes out as a straight line, that's when you can make a conclusion to say it's what? The reaction of the second order. Okay. So how do you now get to predict the half-life? How do you calculate the half-life in the different orders of the reactions that we've talked about? How do you get to predict the half-life? Okay, so I believe by now you are exposed to the equations. You already know the equations. So I'll start with a zero order reaction. How do you calculate the half-life? I believe we know that the half-life is actually the time that is taken to reduce the concentration or a mass of a substance by half. So if you have 2 molar concentration, the time that it is going to take for it to reduce to its half, that is going to be what we are going to call the half-life. Okay, so we know that our equation is this. Okay, let me write it in terms of this. So what you're dealing with is these are concentrations. Okay, so what is our equation? So for us to understand it better, or now we are going to determine the half-life formula, because I don't want you to master formulas here. I just want you to understand how we come up with them. So let's say the initial concentration there, so I'll maintain minus KT. Then I'll put T1 over 2 to show that we're trying to find the formula for the half-life. So let's say the initial concentration was X. So we know that it's a time that it's going to take for it to reduce to its half. So its half is going to be X over 2. That's the final concentration. So now we're trying to find the formula for the time it's going to take for the initial concentration of X reduced to X over 2. Okay, so that's what we're trying to do. So where there is X, remember we are just putting X to represent the initial concentration of A. Okay, so our goal is to make this a subject. So let it be the other side so that it becomes positive. So it will be K 1 over 2 equal to, this one can go the other side. So we are going to have X minus X over 2. Okay, so if you subtract, what are you going to get? So X minus X over 2 is going to give us X over 2, because this is 1 minus half. It's going to be X over 2. Okay. So from there, that is going to be equivalent to what? So what is going to be K T1 over 2 is equal to X over 2. So our goal is to make T, which is representing half-life, to be equal to that. So remember where we had put X, it was just denoting the initial concentration. So we can put A initial concentration. So if you divide by K, it's going to be 2K. So this is actually the formula of what? That is the formula of the half-life for the zero order reaction. Okay, so all you have to do is just know this equation. That's all. Let's talk about determining the half-life of a first order reaction. So for a first order, we know the equation is dependent on the natural log. Okay, so it's Fi, no? That's our formula. Okay, so we are going to put we are going to say our final concentration is going to be half of the initial. So it's going to be natural log of A initial over what? 2. So we'll put a half there to show that it's half-life. Then we have plus natural log of what? A initial. Okay, so our goal is to make this the subject. So we can collect the like terms. So we have natural log of A initial over 2 minus natural log of A initial. It's being equal to K multiplied by the time representing the half-life. Okay, so at this point, from your logs, we believe you know that whenever you are subtracting, you can factor out the log and you're going to divide what you have now. Okay, so natural log of that is going to be A initial over 2 divided by that. So this is supposed to be equivalent to what we have the other side, K T 1 over 2. Okay, let's have some space. So this is going to reduce to natural log. So the A initial there are going to cancel out. You remain with the natural log of what? 1 over natural log of 1 over 2. This is equal to K T 1 over what? 2. Okay. So now our goal is to divide by K so that we make TF the subject of the formula. So our TF is going to be equal to, so if you look at that, we have 0.5 in brackets there. Okay, so natural log of that, what is it going to give us? Okay. So that is the same actually, that is going to give us something like this. So we can express it to be natural log of 2 over what? Over k as our formula for the second order reaction in terms of the half-life. Okay? That's the way you give the half-life of the second order, the first order reaction. So it's independent of, so there's actually a negative there. It is independent of the concentration. Okay? There is no concentration in the formula. It is only dependent on the constant k. Okay, then finally for the second order reaction, for the second order where you have 1 over, so in this case our final is going to be initial over 2. Okay, so our goal is to make t there to be the subject. So this is the same as 2 over a initial being equal to, so that other one is supposed to come this other side, so minus is equal to kt1 over 2. Okay, so what are we going to have? So we have 2 on top here, so we are trying to subtract. So we have a initial as a common factor, common denominator there. So what we're going to have is we're going to have 2 minus 1 is equal to kt1 over 2. So we're going to have 1 over a initial is equal to t1 over 2. So you divide by k. So this is the formula that we're going to be working with when determining the half-life of a second order reaction. Okay. So that's it for this video. I just hope that I've given you tips and ideas on how to deal with chemical kinetics. Okay. Watch out for the next video that is going to deal with a tutorial on how to attempt questions on chemical kinetics, as well as a tutorial on the Arrhenius equation and other parts that have not been covered. But most of the things have been covered. Thank you very much for watching.